Hi, everybody. Today's lecture, we're going to explain the concept of impedance. Okay, so what's impedance? You know from Ohm's law previously that the voltage is equal R times I, or you can say the current is equal voltage divided by R. Ohm's law, you applied before, it was just for resistance. We are trying to find a general Ohm's law that you can apply to other elements like inductors and capacitors. So let's say Ohm's law, we're going to modify to the voltage, and we're going to use phasor, is equal to Z instead of R times I. And also the current will be equal to the voltage divided by Z. So Z, we call it impedance. So we replace in Ohm's law the resistance by the impedance. What is the difference? Well, the difference between the resistance and the impedance, R is a scalar, just a real number. Z, the impedance, it could be complex, could have real, imaginary. Okay, so that's the Ohm's law when we have impedance. So impedance, similar to the resistance, you can say that the resistance, if you want to find the resistance of resistive element, you will say divided the voltage across the resistance by the I across the resistance. That's okay. In impedance, it's very similar, will be the voltage across the impedance divided by the current in the impedance. And observe that I use here phasor, because it could be in general complex number. So let's start with the first element, resistor. In the resistor R, if you have resistance and the voltage across the resistance is equal to VR of T, and the current through the resistance is IR of T. Assume that the voltage across the resistance is sinusoidal, so Vm sine omega t. If you want to express it as a phasor, as we explained last time, you write capital V, R, the maximum value, and the angle is equal to 0. Why? Because you have sine omega t by itself, so it will be an angle 0. And if you represent it as a phasor, you will make like a vector on x-axis by the length of Fm, and that would be the representation of the voltage phasor. How to find the current in the resistor? We are going to use Ohm's law, but apply to the impedance. So we say the current in the resistor is equal to the voltage across the resistor divided by the resistor. That will be equal to Vm on angle 0 divided by the resistance. You get Im. What's Im? Im is equal Vm divided by R on angle 0. What does it mean? It means if you want to represent the phasor of the current, it will be Im on angle 0. It will be the same, in the same phase with the voltage, and you write IR. So both the R in the same direction as phasor. There is no phase shift, and the magnitude of the current is equal Vm divided by R. If you want to express it in time domain, it will be easy, because what you're going to do, say I will be equal I maximum, as you see in the phasor here, sine omega t. So that's the current in the resistor, and that's the voltage across the resistance. Observe that both sine omega t, no phase shift, they are in phase. The only difference is the magnitude. The magnitude of the voltage is Vm, the magnitude of the current Im, and Im is equal Vm over R. And if you like to sketch the waveform, that's the time, and that's the magnitude. For the voltage, that's the voltage. And the maximum is Vm. So this waveform represents the voltage across the resistor. The current is the same thing. It's just Im sine omega t. So you can do it in this way. We'll be starting with the voltage at the same point, maximum at the same point, minimum at the same point, zero at the same point, and that will be IR. And the magnitude is Im. So what do you observe? In phase, you start at 0, the maximum at the same instant, and 0 at the same instant, minimum of both at the same instant, and 0 again. So we say that the voltage and the current, they are in phase. So let's say that the voltage of the resistor is in phase with IR. So the current in the resistor is in phase with the voltage of the resistor. Means there is no phase shift. Okay, let's take an example. Let's assume that we have resistance equal to 5 ohm, and we apply voltage to, or the current in the resistor. Let's say the current in the resistor is equal to 12 sine omega t minus 18 degree ampere. Find the voltage across the resistor. Okay. Observe that the current is given in time domain, 12 sine omega t minus 18. To find the voltage, we know that applying Ohm's law, say that the voltage across the resistor is equal to resistance times the current in the resistor. That's if in time domain. If you make in phasor, say VR phasor is equal R IR in phasor. Okay. R is equal to 5 ohm. It's given here, 5 ohm times IR. IR is given here as time domain. So how do convert it to phasor? Well, this one will be IR. That's the way we write it, phasor. In the textbook, you'll find that IR written as bold letter. So IR is equal to 12. That's the magnitude, and the angle shift, when you look at it, we'll see negative 18. That will be negative 18 amp. So 12 times negative 18 amp. And then when you multiply, 5 times 12 is equal 60, and the angle is negative 18. It will be the voltage. What is that? That's the phasor. How you represent this phasor value? Let's sketch it. But remember that this is the IR expressed as a phasor. So IR is equal to 12 on angle negative 18, and the voltage is equal to 60 on angle negative 18. So both are on the same angle. Let's sketch it. So if this is the X and Y, you make an angle equal 18. This is the line where you'll find both. And then let's say that that's the current. That's IR, which has a magnitude 12 and negative 18. This is the angle. Negative 18, this is the current, which is equal to 12 magnitude and angle in A negative 18. The voltage, on the other hand, the magnitude is 60, but at the same angle, negative 18. So let's choose different color. And we'll make another line. This is the phasor, represent the voltage across the resistance, which is equal 60 voltage and the angle the same one, negative 18. So you see they are in phase. There is no phase difference between the voltage and the current. Great. Let's just take the second element, which will be the inductor. When you have inductor L, let's assume that you have L, and you have current in the inductor, call it IL of T, and this is 0L, and the voltage across the inductor VL of T. Let's assume that the current in the inductor sinusoidal, so you have the maximum value of the current, and let's say sine omega t. If you want to do it in phasor, let's say IL phasor equal IM and angle equal 0. And now I want to find the voltage. What is the relation between the voltage and the current in inductor? In EL 100, we learn that if you have an inductor and the current IL flowing in the inductor and you want to find VL, the relationship is the voltage across the inductor is equal to L times di by dt in the inductor. That's the basic relationship between the voltage and the current in the conductor. Well, we know that, let me just write again, the current was given Im sine omega t. We ask ourselves how to find the voltage. First, you differentiate the current with respect to time and then multiply it by L. So let's do that. Differentiation of the current with respect to time. Im is constant, and differentiation of sine omega t is cosine omega t times the differentiation of omega t, which is equal to omega. Rearrange this equation, you will have omega Im cosine omega t. That's di by dt. Observe that we use sine omega t to represent the phasor. However, here cosine omega t. How you convert from cosine omega t to sine omega t? We know that cosine omega t is equal sine omega t plus 90. So let's use this relationship to plug it in the di by dt. So di by dt is equal to omega Im, and I replace cosine by sine omega t plus 90. That's di by dt. Just let me remind you why we try to find di by dt, because the relationship of this voltage across the inductor is equal to L di by dt. So now what it's supposed to do, I multiply di by dt by L. So the voltage across the inductor is equal L di by dt. I multiply this equation just in the top here by L. So be omega L Im. Let's do that. Omega L Im sine omega t plus 90. That's the VL. Okay, so just let's write it here. The voltage across the inductor is equal omega L Im sine omega t plus 90. this will be considered as the maximum value of the voltage for VL. So we may write it in simple form. I call this one Vm sine omega t plus 90. So I have the voltage and I have the current that was given. Well, let me write it down here. IL of time is equal Im sine omega t. And we know Vm, as we just show here, that's the Vm that I replace omega L Im. Let's just write also this relationship. Vm where Vm is equal to omega L Im. Okay, let's work this in phasor. So VL, it will be equal Vm and sine omega t plus 90. Sine omega t plus 90. So how you do that? You make it like an angle 90. Vm an angle 90. Voltage. The current, we did before, just let's write also again. The current, when you look at it here, IL is equal Im sine omega t. So be magnitude Im and the phase shift is equal 0. So we have Im and phase shift is equal 0. And just let's remind ourselves the Vm is equal omega L Im. How to find the impedance? Our refreshing memory. We know in Ohm's law R is equal V over I, but this is a special case. But now we're not working with that. We're working with something more general. Instead of R, write Z, impedance, and the voltage over the current phasor. So it's very similar. That's Ohm's law, the general one. So let's now find the impedance of the inductor. I divided the voltage across the inductor by the current in the inductor. The V across the inductor is equal Vm angle 0. And the current is equal Im angle 0. So when you divide both, what you'll get, Vm over Im 90. But what's Vm? That's Vm. Let's replace it now. So omega L Im and angle 90, you can write it J. Okay, remember, complex number. This is positive J and this is negative J. So positive J is 90 degree and negative J negative 90 degrees. So I divide by J and divided by Im and angle 0, you can write Im. Now doing that, Im cancel Im. So what is the result? The result is equal to ZL is equal J omega L. So the impedance of the inductor is equal J omega L, not like R. The resistance, if you remember, it was real number, but this one imaginary number, J omega L. Another thing, you observe here that the impedance of the inductor depends on the frequency, but the resistance does not depend on frequency. To make it easy, what about if we assume another variable called X, reactance, and reactance, it just will be the impedance without writing J. So it will be omega L. Of course, the unit will be ohm, because the impedance unit also in ohm. So X equal omega L. And since this is inductor, we'll call it XL. So what's XL? It's reactance. And this is the reactance of inductor, the inductor. Or you can say, you can make it, you can call it inductive reactance. Okay, so it's like the impedance but without J. Let's just a little bit elaborate on that. XL is the reactance. So if you make the relationship between XL and omega, so we make an x-axis omega, that's the frequency, and the vertical is XL, and you just substitute some value. If you put omega, for example, equals 0, so what is the value of XL? Will be 0 times L, will be 0. What does it mean omega equals 0? Well, omega equals 0, it means DC. So DC, the frequency of DC is equal 0. XL will be equal 0 ohm. So what does it mean XL is equal 0 ohm? It means short circuit, like switch closed, short circuit. So in DC, the inductor behaves as a short circuit. The value is 0. And when you increase the frequency, like take any value, you'll find increasing. Every time you increase the omega, XL will increase because XL is equal to omega L till you reach infinity. So infinity times L will be infinity. So it's like a straight line going to infinity, all right? And the slope of this relationship is equal to L. And in high frequency, that's when you have AC, of course. Like omega reaching to infinity, you'll find that the inductor behaves as an open circuit, right? That's the inductor, all right? Just I want you to find this relationship because it's important application. So that's the reactance of the inductor, and that's the impedance, which is equal J omega L. Remember that the impedance of the inductor depends on the frequency and depends on the value of L. So every time you're increasing the frequency, the impedance increasing. You increase the value of L, the impedance increasing, okay? And you can deal with the impedance as a complex resistance. Let's take a numerical example. Let's say that we have an inductor, and this inductor is equal to 0.1 Henry, and has a voltage across. The inductor is equal to 12 cosine 60t plus 15. Oh, it's not clear. Let's make it big. The voltage across the equal to 12 cosine 60t plus 45 degree voltage. And it's required to find the current in the inductor. So the question is determine the current in the inductor. How to solve it? All right. We're going to use the phasor. That's the easy thing. So I'll write the voltage is given. It's equal to 12 cosine 60t plus 45. We know to express any variable in phasor, it has to be expressed in sine. So how can you express cosine into sine? Well, be equal 12 sine 60t plus 45. Okay, so to convert from cosine to sine, you're going to add 90. And just let me tell you, if you are confused, are you adding 90 or negative 90? You know the relationship between sine and cosine, 90, all right? So if you sketch sine and cosine, this is your sine, and the cosine will be like that. So the cosine start ahead, so it's advanced, so be plus 90. And there is a table I gave it to you last lecture, how to convert from cosine to sine, okay? All right. Why I'm doing that? So I can express it in phasor. Equal 12 sine 60t plus, you have 45 plus 90, will be 5, 3, 1 degree. So what's that? The voltage. I didn't do the phasor yet. Convert now this to phasor. The voltage will be equal to 12. You don't put the frequency, just put the angle. The angle here plus 135. Make it 1 plus 35. This is the voltage across the inductor. Now, I want to find the current. How to find the current? You find the impedance of the inductor L. L is given 0.1. L is equal 0.1 Henry. How to find ZL? ZL is equal J omega L. How to find omega? Look at the expression here. For the voltage, you'll find that 60 T. So 60 T, it means omega T. So omega is equal to 60 radian per second. I just got it from the voltage waveform. So now I can find ZL. So it's equal J. Omega is equal 60. And L is equal 0.1 Henry or millihenry. Let's check Henry. So you multiply by J 6 ohm. That's the Z. All right. I found the Z. Ohm's law said that the current is equal to the voltage divided by the impedance. In this case, the voltage across the inductor, it's 12, and the angle is 135 degree voltage, and the impedance is equal J 6 ohm. What does it mean J? J, it means 90 degree. Remember that all the time. So you can say is equal to 12, 135 divided by 6 on angle 90. You divide the number 12 by 6, but the angle, you say 135, and the one in the bottom changes sign. When you bring it up, it will be negative 90. 12 divided by 6 is equal to 2m, and the angle 135 minus 90, you get 45 m. So this is the current, but expressed as phasor. I'm interested to sketch both. That's the voltage, 12 and 135, and that's the current. Let me sketch it. I will write again here on this page. The voltage is equal to 12 and angle 135, and the current, we just got it in phasor, 2 on angle 45. Let's sketch it. So that's X, so Y, and X represents angle 0. You have the current on 45 degree, so I will do the current on angle 45 degree. That's 45 degree, and equal to the current 45 degree, and the voltage is 12 135, so that will be choosing different color. That's 135, and that will be the voltage. Actually, you will see always that the difference between the current and the voltage 90 degree. If you just sketch it like that, that's the current and the voltage. That's the voltage, and the angle is 90 degree. So observe that. What is the relationship between the current and the voltage? Current lag the voltage by 90 degree if we assume the direction of the rotation in this direction, counterclockwise direction. So we'll say this important result. This result is the current in the inductor lags the voltage by 90 degree. It means that the current always behind the voltage by 90 degree in inductor, always. You see, because if you subtract 135 from 45, find 90 degree. Again, it's very important. The result that we got, what? The reactance of the inductor is directly proportional to the frequency. The impedance of the inductor is equal JXL, which is equal J omega L. The current maximum in the inductor is equal Vm over Xm. I'm talking about the magnitude, right? And the current in the inductor lags the voltage across the inductor by 90 degree. That's a very important result. Great. So let's now explain the capacitor. If you have a capacitor C and the voltage across the capacitor V equal to V maximum sine omega t, and the current flowing in the capacitor is equal I, C. So what is the relationship between the voltage and the current, and what is the impedance of the capacitor? We'll follow the same procedure that we did with the inductor. So that would be like revising what we did with the inductor. Well, we'll write just the voltage across the capacitor. We'll assume it Vm sine omega t. Well, that's the voltage. So the phasor representation will be like just a vector like that, and this is the voltage across the capacitor, angle 0. How to find the current? There is a fundamental relationship between the voltage and the current in the capacitor. The current in the capacitor is equal C dV by dt. So the current in the capacitor is directly proportional to the rate of change of the voltage across the capacitor. So to find the current, first we have to find the differentiation of the voltage across the capacitor. Vm is constant, and then the differentiation of sine is equal cosine omega t. Differentiation of omega t is equal omega, so we might write it like omega Vm cosine omega t. And as you know, we want to always express as sine omega t, so let's say omega Vm, and cosine can be represented by sine omega t plus 90. That's dv c by dt. That's differentiation of the voltage with respect to time. To find the current in the capacitor, we say it's equal c dv by dt. So I multiply the whole equation by c. So you have c omega Vm sine omega t plus 90. The same thing. This thing I can call it Im. So you can write now the expression for the current in the capacitor is equal to Im sine omega t plus 90 degree. All right, that's good really. Where Im is equal to omega c Vm. Okay. Let's now express this current in a phasor. As a phasor, IC will be equal Im angle 90 degree. Im is equal omega c Vm, and that's 90 degree. That's the representation of the current as a phasor. Again, how you find Z? You divided voltage by current, but all should be phasor. The voltage phasor, we have here the voltage phasor, It's Vm sine omega t. It means you have Vm angle 0. The current, we have here just the current. So it's equal omega CVM angle 90. Vm cancel Vm. So the result will be Vm, I'm sorry, Vm is cancelled already, will be 1 over omega c. And this 90 will go in the top minus 90. We know minus 90 is equal minus j. So you can write Z of the capacitor is equal minus j, that's minus 90, times 1 over omega c. That's the impedance of the capacitor. Again, we'll do the same thing. If you like to write ZC without the minus j, you can minus j xc, right? In this case, what's xc? Xc is equal 1 over omega c. Interesting. It's different than the inductor. The inductor was directly proportional to the frequency, but now the reactance of the capacitor is inversely proportional. So if you want to find the relationship between the frequency and the reactance of the capacitor, make a small table, short table. That's omega and that's xc. If it's 0 dc, so you have 1 over 0 will be infinity. What does it mean, infinity? Infinity ohm, like open circuit. So capacitor acts as an open circuit with DC, because the DC frequency is equal 0. If you increase the frequency, then you will start to find reactance value till you reach infinity. Infinity, 1 over infinity is equal 0. So the capacitor acts as a short circuit with high frequency, which will be, of course, as AC. So in AC, it will be like switch, closed switch. So how we make this relationship? At omega is equal 0, it's infinity. So at 0 will be coming from big value here, and then will be decreasing when it reaches high frequency. So the reactance inversely proportional to the frequency, and also inversely proportional to C. Another important factor that we get from this relationship of the phasor, the Vm, we said that the Vm is on x-axis, that is the voltage across the capacitor phasor. What the current we found here? The current is an angle 90, I'm sorry, 90. So let's make the current in different color. So that's the current, IC, and it's 90 degree. So the current is different here than the inductor. The current is leading, so the current in capacitor leads the voltage by 90 degree, opposite to the inductor. The inductor, the current inductor was lagging, but here leads, it's ahead of the voltage if we assume that the rotation in the counterclockwise direction. Let's take a numerical example. We have a capacitor, and the capacitor is equal 10 microfarad, and the voltage across the capacitor is equal 100 sine omega t minus 40 voltage. And that's the current, and the frequency of the supply is equal to 1000 hertz. Determine the current in the capacitor. Well, we know that to find the current in anything, we have to divide the voltage by the impedance. I have the voltage, yes, I have the voltage. What's the voltage here? It's given. First, let me write in time domain. It's given the voltage as 100 sine omega t minus 40 degree voltage. In a phasor, will be equal 100 angle negative 40. It's already given in science, it was easy. Now, I want to find I found the voltage, now I have to find the impedance. The impedance of the capacitor is equal minus j 1 over omega c. So I need omega. Omega is not given, but the frequency is given. I know that the relationship between omega and the frequency f is equal to pi f. So equal 2 pi, and the frequency is 1000 hertz. So it will be equal to 2000 pi radian per second. So that's the omega. Now I have omega and I have c. C was given 10 microfarad. So now I can find ZC. ZC will equal minus J 1 over omega 2000 pi times 10 microfarad. It means 6. Let's just calculate this value. So you have 2000 times pi times 10. That will give 15.9. Don't forget you have minus j ohm. So that's the value of the impedance. This is 1, okay? Negative j 15.9 ohm. Once we do that, it's easy now to apply Ohm's law. I is equal V over Z. Using phasor, I remind you. So I, phasor, and capacitor. The voltage as a phasor, it's given here in this equation, 100 on angle negative 40. Don't forget to put the unit. The impedance, I just got it there. So minus 15.9, and I know minus j, it means minus 90 degree. Oh, so how I have a minus here? You can have both minus, because already the all minus j, I make it minus 90 degree. You don't put minus here, okay? Equal. I divide the number by itself, 100. I divide it by 15.9. And the angle, the one at the top, negative 40, and the bottom, negative 90. When it go up, it would change to positive 90. So let me divide 100 by 15.9. 15.9. That will give 6.29, and the angle 50. And that was the current in M. That's as a phasor. All right. Well, if you want to express as a time, IC will be 6.29 sine omega. Now we have omega, by the way. This is your omega. 2000 pi. Can leave it like that. T, omega t, plus the angle here that you got, 50 degree, and the unit is M. So express both as a phasor and as a function of time domain. I'd like to sketch the relationship between both. That's omega. I'm sorry. I'm making the relationship between the phasor. So that's the current phasor. 6.29 on angle 50. So let's say this is 50, and that's the current, 50 degree. And the magnitude is equal 6.29. About the voltage was given 100 on angle negative 40. 100, let's take another color, 100, negative 40. That will be negative 40. You see, it's 90 degree again, and that's the voltage. So that's true. And look at that. The current is leading, the current ahead of the voltage by 90 degree. So it means that your solution is correct. Okay, we're done with the lecture today, but there's an interesting problem. Let's say that question. Let's say that you have voltage given as 100 sine omega t plus 40. All right. And this voltage was across an element, unknown element. So that was the voltage across. And the current, when it was measured, was equal to 2 sine omega t minus 50 m. So the question is, what is this element? Is it C or L? Is it inductor or capacitor? After you answer this question, what is its value? It means if it's inductor, how many Henry? If it's capacitor, how many Farad? So how to solve this question? Actually, the solution is really easy, because all it's supposed to do, find the impedance. And you know the impedance is equal the voltage divided by the current. The voltage here in phasor, 100 sine omega t plus 40. So it's equal 100 in angle 40. The current is equal to, the magnitude is equal to, and the angle negative 50. That's voltage, that's amp. When you do that, you'll find that the impedance is equal to 100 over 2 is equal 50. And you have 40 degree, move the negative 50 up, will be positive 50. That will be equal 50 on angle 90. It means J50 ohm. So that's the impedance. So the element now is clear that its impedance is equal to J, positive J, and positive J happen only with the inductor. So I'll say since Z, the impedance, has positive J, it's inductor. Actually, you can answer this by inspection. When you look at the voltage is on angle 40, right? Angle 40, that is the voltage in angle 40. And the current on angle negative 50, just let me make space here for, so, oops. So if I make just a quick sketch here, that's 40. That's the voltage, and the current is negative 50. So the current is lagging the voltage by 90. So obviously it's inductor, because the current lags the voltage in inductor only. And this is another way. So you can do by inspection. You can, but I'm using this because it will help me to find the value for the inductor. So I said that's inductor, and I know that ZL, we did before, is equals J omega L. So omega is given, should omega be given? So let's say in this problem that omega is equal to 1000 pi radian per second. So J 1000 pi L, that I don't know, should be equal to J50. So it means that 1000 pi L is equal to 50. So L is equal 50 over 1000 pi. It's a small number, so I can multiply it by 1000 to get in millihenry. Doing this fast calculation, we get 15.9. Yeah, there's no space. So it'll be equal to 15.9 millihenry. That would be the answer, right? That's it. And you're going to have in-class practice today in your